you looking there?
Looks great.
See if I can hide some of the hide floating meeting controls. There we go. Okay. So, I'm going to talk a bit today about the Great Unconformity, which is a subject that I sort of stumbled into working on, and I'll talk a little bit about how, as well as some sort of a setup, background, my perspective on all of this, and then a conclusion. We're going to start with some historical context. So, what is the Great Unconformity? Where was this term first used? And what did it refer to then? How has it evolved over time? What are some of the things people have written about this, either individual unconformities or about the broader phenomenon over time? Then, yeah, how I started working on this. We're going to spend a bit of time in the middle before we get into the really nitty gritty. Uh, Going back to terminology. So, like, what do we mean when we say this? Because I think some of the debate about this topic right now is, in a sense, a conflict of terminology. And hopefully that will be worthwhile to talk about. Then we'll go back a bit to the geology and wrap up with more historical context. Okay, and we'll see how long this takes. Okay. All right. So when you think of the Great Unconformity, many people probably think of the Grand Canyon. So this was discussed by John Wesley Powell, though not under this name, interestingly. When Powell floated the Grand Canyon, they talked at some length and somewhat poetically, actually, about the various unconformities in the canyon. So, in the very depths of the canyon, we have black granite. Above, there's this package of broken, ragged, non-conformable rocks. So by that, what we would now call the Grand Canyon supergroup. And then above that, we have conformable horizontal beds. And there, yeah, this is government publications, which this is, aren't don't generally sound this poetic anymore. But one might imagine that this was intended for the Library of the Gods, and it was. The shelves are not for books, but for the stony leaves of one great book. So that's good fun. In describing this figure at the right here, well, this package up here was at the time thought to be Carboniferous, generally not correct. It's Carboniferous up there somewhere, but not this near the unconformity. But below that, it's between the periods of the deposition of this series B to B prime and C to C, we have a period of erosion. Um, and again, the poetic language, what plants lived here, we cannot learn. What animals roamed over the hills, we know not. And yet there is a history which was not lost. Okay, so this is, they're describing the Great Unconformity here, but the term was not yet coined. That was actually a little bit later. Also, there's something kind of wrong with this figure. You may notice that lower contact there. That's probably not geologically plausible. But anyways, what a few years later we get Dutton 1882, which has both a very nice figure and a lot of a sketch from the outside of the canyon and a lot of discussion about what now they start calling the Great Unconformity. Which here, that's this one, right? So this is what we would now call the Tapete Sandstone, at the time still thought to be Carboniferous. Oops. But so there's the description of this. Carboniferous theories is conformable. Then you get this quartzite at the base, and there's a cliff former there, and then below you get variously either what they then called the Archean schist, so the it's not Archean, but the Vishnu schist, or otherwise you get these angular unconformity with the tilted beds of the Grand Canyon supergroup. So that's where the term was originally used, and that's why we always tend to associate it with the Great Unconformity. Um, we'll come back to the terminology a little bit later. For now, we'll just talk about some of the subsequent discussion of similar unconformities, albeit not under that term. So Charles Walcott, is famously associated with the Burgess Shale, was very concerned with what he called the abrupt appearance of the Cambrian fauna on the North American continent, or what we would now call the Cambrian explosion. And this was a problem in the context of gradualism. They didn't have evolutionary concepts like punctuated equilibrium yet, so abrupt appearance was almost catastrophism. This was a problem. And Walcott's solution was, oh, there's an unconformity here. That's very convenient. He went so far as to say that everywhere there's a stratigraphic and time break between the known Precambrian rocks and Cambrian sediments. Okay, also, it turns out not quite true, but he was to some extent onto something. There is often an unconformity here. Certainly not everywhere, but often. And again, yeah, he coined this term Lipalian, the something like the overlooked era, for the era of unknown, what he called unknown marine sedimentation. So essentially, what was happening during this gap, this unconformity here. Um, so this term was used for a little bit, but never. It's not something we talk about often today. It's kind of fallen by the wayside. If we go a few years later, sort of one of the we're getting now into the mid 1900s. This is paper by Walter Olson, an American scientist, where again talking about the origin of the Cambrian unconformity. References here, the Walcott's Lipalian. And Olson's idea was that this was megatides. So we didn't actually know the age of the moon very well at the time. One of the hypotheses was it was captured perhaps relatively recently, and he proposed that at the time tides were 8,000 times higher than at present, attaining amplitudes comparable with present mean ocean depth. And these tides would sweep across the interior and laden with sediment and rock fragments, abrade the land surface and reduce the continents to peneplains. Well, okay, that's fun. A few years later, we landed on the moon. Turns out it is much older than that. It's been with the Earth for a long time, and we did not have tides like this in the early Precambrian. So that's probably not it. And then there wasn't much discussion about this for a while. There's one caveat, which I'm going to come back to at the end there. Sort of until I would say really the work of Shannon Peters. So around 2012, we have this paper, Peters and Gaines, Formation of the Great Unconformity as a Trigger for the Cambrian Explosion. And this was based on Shannon's work developing macrostrat, which is the digitization of a lot of pre-existing um, geological generalized strat columns for North America, the Cosuna charts. And what Shannon and Robert observed here is that Cambrian sedimentary rocks were unusually likely to sit unconformably atop basement. So one of their figures is just the area of basement before you get sedimentation of, let's say, lower Cambrian, middle, later Cambrian, Ordovician, Silurian, etc. And there's this peak in the Cambrian. The Cambrian rocks are unusually likely to sit right on top of sedimentary rocks, are unusually likely to sit right on top of igneous or metamorphic basement. So that's an interesting observation. Um, there are also you can also extract from macrostat various metrics for sedimentary rock volume or area. So here's volume. Macrostrat is just a North American data set. So we have two sort of comparisons here. Below we have macrostrat. So this is macrostrat just North America compared to the older, lower resolution but global data set of Alexander Ronov. So that's those two red lines. Ronov also has a global estimate, and then here this blue line. This is just the blue macrostrat line is just macrostrat scaled up by the relative volume of all of the continental crust, all of the exposed continents relative to the area of all the exposed continents relative to area of North America. And that actually agrees pretty well with the Ronov global estimate. So perhaps, the fact that we were only looking at North America is not the thing that's responsible for this signal. This is not a North America only phenomenon. So that's preserved sedimentary volume. Um, Here is area. So area proportion of the continents, fraction of the continents covered by sedimentary rocks as a function of time. So here we have the macrostat record, which goes back a bit farther. We also have a few other records that are global, but Ronov, these other two, global, but don't extend as far back in time. But again, they generally overlap with this North America only macrostrat record. So to me, this is what sort of established in the modern period that the Great Unconformity, there's something there. This isn't just a name we gave to a pretty unconformity in the Grand Canyon. There's some broader phenomenon associated with unconformities across the Phanerozoic Proterozoic boundary. And we'll come back to that again when we get to the terminology. Oh yeah, and so this is log scale here. This preserved sedimentary rock volume. If you plot this not in log scale but in linear scale, it's perhaps even more obvious and perhaps has some implications for, if you want to explain this step, the older sedimentary rock has to be either eroded away or for some reason never deposited. If we increase the amount of sedimentary rock that is preserved on the continental crust or deposited on the continental crust, well, you could do it that way, or you could do it by eroding away older things. Okay, so we'll come back to that. I did not set out to work on this. As you may have heard if you heard my previous talk a couple of weeks ago, originally started as a uranium-led TIMS geochronologist and petrologist. I did a lot of work in my PhD on secular evolution of Archean continental crust, and thought a lot about zircon. As someone who's working in a TIMS lab. which is this really nice mineral, crystallizes with lots of uranium, very little lead, so you can date it precisely. One of the other things that you get in zircon is hafnium. So hafnium is similar chemically to zirconium, the main ion in zircon. So hafnium substitutes into zircon at sort of weight percent levels. Uh, Lutetium, which decays lutetium-176, decays into hafnium-176 with a very long 37 billion year half-life. Lutetium is not compatible in zircon. It's only there at the ppm level. So with respect to the lutetium-hafnium system, zircon is kind of the opposite of a chronometer. It locks in to some extent the hafnium isotope composition of the magma from which it crystallized. There's slight additional ingrowth, but you can easily correct for that. And so it lets you see something about the isotopic properties of the magma from which that zircon formed. So I was interested in this, started compiling data originally with an eye to thinking about the same sorts of problems I talked about last time. So, the degree to which we have plate tectonics through time, changes in Wilson cyclicity. I was sort of expecting we would see a lot of sort of Wilson cycle sort of wiggles in this data set, which arguably you do. But that ended up being sort of a secondary point when we started compiling this data. So this was back in the sort of late 2010s at this point. We compiled a bunch of data from a number of existing compilations, primarily looking at either hafnium isotopes or oxygen isotopes in zircon or both. Got a total of some tens of thousands of samples and applied the same statistical techniques to this that we used when we talked last time about evolution of the composition of the continental crust over time. So we used this weighted bootstrap resampling approach. One important caveat here is compared to the whole rocks, with the whole rock data set, we had quite good latitude and longitude constraints for almost every sample. With this zircon data set, this was not the case, just based on the data that was in the previous compilations. In many cases, the only data we had for location was, a string, a name of a continent. So we were not able to do the weighting based on spatial scale, just the weighting based on temporal density. But nonetheless, you can apply this. We have very good temporal constraints because these are all on zircons. They're all directly datable. If you apply this method, here's sort of the curve we get. Uh, so again, just for context, so these lines here, depleted mantle going up through time, that's because the mantle has more of the parent than the crust does. And more of the parent than even the average Earth. So sure, this flat line there, that's chondritic undifferentiated reservoir. That's what we think the average Earth, bulk Earth, probably is. The mantle, since lutetium is more compatible than hafnium, the mantle goes up over time because it's got more parent isotope. The crust goes down over time, with some limit of if you had no lutetium parent at all, you would go down along that line. So our data generally falls within these lines. You can calculate the average. We're now zoomed in on the scale a bit. We're still on average somewhat near this Chur line, which is, I think, interesting from a tectonic perspective. It's telling us that throughout this whole time, we are apparently mixing similar proportions of mantle input and crustal recycling into the magmas that make our zircons all the way back to the Hadean, which is interesting to me. And we do see these sorts of variations, which I would imagine have something to do with the Wilson cycle. If you do spectral analysis of this, the periodicities do look a bit about right. But what grabbed our eye when we did this was this feature here, which is much more rapid and dramatic than most other things in the record. So if we're thinking in this hafnium isotope space, epsilon being deviations from the Chur average Earth standard and parts per 10,000. So positive things have more mantle, negative things have more crust. This negative spike is we're putting a lot of old felsic crust into new magmas, one way or another. And geochemically, petrologically, there's a few ways you could do that. One option would be if you go to the deep crust where temperatures are relatively high, perhaps you have some amount of crustal assimilation, perhaps anatexis of the deep crust from if you bring in some mafic magmas that are hotter than the solidus of the lower crust. Perhaps you can do that. You could imagine this happening in, say, like a transcrustal magma system, a deep crustal hot zone, the classic Annin model. So maybe down here where you're very hot, you could do this. You can't do this very well in the upper crust, actually, not at scale, but in the deep crust, sure. The other thing that comes to mind, which something I thought a lot about, given thinking about things like atacites in both an Archean context and the context of like my undergrad advisor Sue Kay's work, the Andes and Aleutians, sediment subduction as well as subduction erosion is a great way of getting crustal material into your magmas. So sediment subduction, this is you have some sort of eroded crust sitting on top of your subducting seafloor. It gets carried down with the plate, down through the trench, through the gets dragged through the accretionary prism. Uh, but then this is on average more felsic than your basalt, so it does not invert to eclogite. It does not sink down to double prime. Instead, it is relatively buoyant, may partially melt, may mix into your new magmas, will participate in mantle flux melting, and also may rise diapirically through the mantle wedge in the subduction zone in a process called relamination. So the sediment, if you subduct it, you're taking it to where the heat is, and also there's water because you're in a subduction zone. So this is a great way to melt a lot of crust. Just instead of like this case, we're bringing the heat to the crust. Here we're bringing the crust to the heat. Okay, so in this case we also get water. So petrologically, I kind of already like this a little bit, but to test this in a quantitative way, um, well, we wanted to look at a few things. So, well, does this work out? Just sort of back of the envelope today. If you look at average zircon epsilon hafnium of recent magmas, last few tens of millions of years versus modern day trench sediment thickness, how much accumulated sediment is sitting on top of your downgoing ocean slab in the trench. And there's a pretty clear correlation. Granted, we have a lot more data at the left side. Most trenches have these relatively thinner sediment coverings than up when we get up to the 5 or 6 kilometers. But our trend is there. If we want to distinguish these two, the other thing that was obvious to me as a test would be oxygen isotopes. So the mantle has a relatively consistent oxygen isotope value, about 5.3 in delta 18O. Low temperature meteoric alteration. So if you take a silicate rock and expose it to the ocean, expose it to rainwater, weathering, that tends to push things up. So if we're this is all just happening in the mantle, or it's happening in the deep crust driven by mantle magmatism, we should expect a relatively flat trend. If we have an input of material that has been eroded, subducted, uh, and then put into your new zircons, we should expect maybe this low temperature meteoric alteration signal to correspond with that hafnium isotope signature that we saw. So in fact, this is what we saw. Here's just lining up the two time series. Your hafnium, your negative hafnium excursion corresponds with your positive isotope, oxygen isotope excursion here. So suggesting that this component that you're remobilizing into remelting into new magmas to make your zircons is both low in hafnium and high in oxygen. Um, so that's intriguing. We can look at this a little more quantitatively if we just sort of standardize these ratios. So D trend, unit mean, and then look at the covariance. I'm going to breeze through this a little bit in the interest of time, but the point is we get this sort of quantitative signal that's quite distinct, especially if we look at the degree of covariance relative to the slope. So essentially this pulse you have the decreasing hafnium and increasing oxygen, and then this pulse here, essentially it's the recovery, the back to normal. Okay, so this is a geochemically to me significant signal. Has a pretty clear interpretation geochemically. There's only one problem, which is that if you just do a sort of back the envelope mass balance for how much crust you need, so if you say, let's say the average continental crust at this time, at the time of this nadir, it probably has an epsilon hafnium of about minus 35 based on our same convenient hafnium isotope and zircon data set. If you want to do this by mass balance, you need to subduct, or well, if it's remelt in one way or another, something like 2.4 times 10 to the 8 cubic kilometers of average crust to make this signal for this duration, given average rates of crustal magmatism. That's a very abstract number, but if you just do a little bit of math, divide that by the area of the continental crust, that's equivalent to a height of 1.6 kilometers spread out across the whole continental crust. So our thought at this point was, shouldn't we have noticed something missing? And this is around the same time I was seeing Shannon publish more and more of these sorts of curves and show at conferences that, oh well, there is this event sometime around the Phanerozoic Proterozoic transition where you have a big change in what is seemingly happening to sediment across this time period. Um, so perhaps this is two sides of the same coin. Um, that would favor, this option out of those two interpretations of the sedimentary volume record. Okay, so but before we get too excited about this, let's go back to this terminology. Okay, so I'm going to go through a few different possible definitions, their meanings. 'Cause there's been a lot of discussion about, oh, great unconformity or great unconformities, plural, or are these synchronous or diachronous? Is this one unconformity composite? Well, okay, so if we start with the original, Dutton's usage of the term, it's the unconformity below what we now know as the Tapete sandstone. Um, I guess that's sort of one unconformity. It changes a little bit from place to place. This is certainly diachronous where it's, where say the sub Tapete's unconformity has captured the older sub Unkar unconformity and is a basement nonconformity. Then it's clearly diachronous and composite. If it's just the Tapetes um, on top of the Grand Canyon supergroup, then well, it's an angular unconformity. Could be like, there's probably still some element of diachronaity. There's a lot of missing time. Um, less clearly so than in this case. But whether this really depends on the local geology. If you want to talk about those two bottom questions there. Okay, so that's the original usage. I think there's sort of two obvious generalizations of this that have sometimes, I think, cropped up or been used or implied. One would be time-based extrapolation from this original usage. So, if this was the one below the Tapete sandstone, we might say any unconformity spanning the Cambrian-Precambrian boundary is the Great Unconformity. Um, well, there's tons of different ones in different places. There's no more than one in any given location. It's kind of by definition semi-synchronous. It has to span the base of the Cambrian, but the start and the end are probably very diachronous. And this is completely variable as to whether it's composite or not. Probably in many cases is. Another extension is you might say, because in at least in uh, some of the most profound instances, this sub Tapete's unconformity has captured the older basement nonconformity. Sometimes people will say, and there is, as Shannon mentioned, often a basement nonconformity below the Cambrian. Some people may say that, oh, any basement nonconformity, that's what we're going to call the great unconformity. Again, this is very different in different places, but no more than one at any given place. This is totally diachronous, from place to place. There's no expectation that every basement nonconformity is the same age. Um, and generally composite, probably almost always composite. Uh, all right, but neither of these are really the way that I tend to use the term. I more follow Peters and Gaines, which I think would be best summarized. The main point there is this phenomenon that the subcambrian unconformity often exists and is often a non-conformity. That phenomenon as a phenomenon that's singular. And well, the phenomenon it's neither of these are really applicable. If you go to an individual unconformity that makes it up, non-conformity or otherwise, it may be either synchronous or diachronous or composite or not. But the phenomenon is what we're discussing here, which is a different point in that case. So let's talk about that a little bit more because I think that's a useful way to think about the great unconformity as something that we will discuss, a cause of or a nature of. These two are sort of too heterogeneous individually to say much about. Um, so we'll talk about this. Okay, we may talk about the phenomenon that subcambrian unconformities are common and often non-conformities. So essentially this figure from Shannon, or in other words, that Cambrian sedimentary rocks are unusually likely to sit unconformably atop basement. That's an interesting observation. Um, Relatedly, um, this actually, I would say, implies an increase in continental sediment coverage across the Phanerozoic Proterozoic boundaries. So if these Cambrian rocks are sitting atop basement, that means they're not sitting atop other sedimentary cover. So we have to have an increase in the proportion of the Earth covered by sedimentary rocks at this time, and vice versa as well, right? So if we have this increase in the proportion of the continents covered by marine sedimentary rocks, well, this increased coverage that we get in the Paleozoic, it's again because the coverage is lower back here, it's not generally sitting on older sedimentary rocks. It's got to be sitting on, well, what's the alternative? Basement. Okay, so these two are very linked, and worth consideration to me. Demand some sort of explanation. These are consistent with, though not exactly equivalent to, the related increase in sediment volume flux across the Phanerozoic boundary. So this trend that's from both Macrostrat and Ronov, it's about factor of 5 increase in the volume of preserved sedimentary rock here. Um, it's certainly consistent here. You can see how if you had an erosional event, you could cause both of these phenomena. Um, it's not the only way you could do it, but that would be one consistent way to explain all of this. Um, Interestingly, this sort of definition in the box here also implies widespread exposure prior to the deposition of the Cambrian. So, right, so if these are being deposited on basement, well, those had to be exposed. Those had to be not covered by previous sediments. So that's implying that there's some sort of synchronicity in the existence of an exposure and or erosional surface. So that's one of the things Shannon calls this, synchronous exposure surface. And I think this sometimes causes confusion, and that this is not saying that every unconformity spanning the Cambrian boundary is synchronous, or every basement nonconformity is synchronous. But if this phenomenon is real, then it is implying some level of consistent exposure in at least the places that produce this phenomenon here. Notably, this does not imply, I'm gonna belabor this a little bit. This does not imply that any individual physical unconformity surface, even if it's one contributing to this phenomenon, is not composite or is produced by only a single episode of erosion or non-deposition, right? Most unconformities in the real world are composite. Arguably, almost all, if you consider things from a Sadlerian perspective, right? Deposition is unsteady. There's tiny non-conformities everywhere in the sedimentary record. So you're probably almost always capturing some previous unconformity at any major unconformity. And in really big ones, basement nonconformities, you're certainly often capturing multiple episodes of erosion. But that doesn't mean we can't talk about this phenomenon, and doesn't mean this phenomenon is not something with a definite cause. Okay. So coming back to this, if we're going to discuss the origin of the Great Unconformity, these two, it's not really meaningful to discuss the origin of a singular origin for these, if those are what you mean by great when you say Great Unconformity. Because yeah, these are diachronous, they're composite. Um, Not really meaningful. However, you could, in principle, talk about a singular cause for the Dutton unconformity. You definitely could talk about a singular cause for this sort of broader phenomenon. And I'm generally doing this when I talk about the Great Unconformity as a singular thing. Okay, so with that in mind, this is a remarkable phenomenon. This is quite non-uniformitarian, actually, and let me explain that a bit. So, if we think about constant sediment accumulation rate, so this is no erosion, we're just accumulating sediment on the continental crust at zero point 0.9 cubic kilometers per year. In age versus preserved sediment flux cubic kilometers per year, it's flat. Okay, obvious. If we want to produce a step change in this, the easiest way to do it is with a single episode of erosion. So let's say this is a discrete episode of erosion. So just one episode, n equals one, synchronous. With a likelihood of eroding any previous rock of 80%, zero point 0.8. So that gives us this, about factor of 5 singular step in preserved sediment flux at whatever time this singular erosional event happened. So that's one way to make a step change. If you have more than one of these events, if this is not something sort of rare, well then, okay, you're going to get more steps. So let's say here's when if you stack up two events, each with a likelihood of eroding pre-existing sediment uniformly of 0.7, we can sort of keep increasing the number and decreasing the likelihood until we converge upon an exponential survivorship curve, which is sort of uh, I think Shannon's and also my background expectation for what preserved sediment volume through time should look like. It should be a continuous survivorship process, following an exponential law here. The fact that we don't see this is implying that what we're looking at is not the product of just continuous normal erosion, and also not the product, given that there's sort of one big step, not many steps throughout time. This is not something that happens regularly. Every time you break up a supercontinent, this is to get this step. This is a rare event. This is a non-uniformitarian event. Um, so how do we get a non-uniformitarian event like this, we need, to me, a non-uniformitarian cause. And the most obvious one to me in this time period is snowball Earth. This is one of the most dramatic and non-uniformitarian things that's probably ever happened on Earth, where we're thought to have glaciated the Earth all the way down to the poles or all the way down to the equator from the poles, including the oceans. So there's the Sturtian and Marinoan, two snowballs in the Cryogenian. There's also some later, smaller non-snowball glaciation throughout the Ediacaran that may be interesting to consider. But these two big ones are really quite dramatic, and they're going to have a lot of consequences, both for for life on Earth, for nutrients, for well, so many things. One of the things they will do is, well, if they glaciate all the continents with Antarctica-style glaciers, they're going to draw down sea level, and there's at least the possibility for glacial erosion. So glaciers are known to be relatively good drivers of erosion when there's gravitational potential energy available. So if we look at the mountains, there's this famous glacial buzzsaw effect. Originally, Stephen Porter pointed this out, but it was only published in a compilation by Broker and Denton. Essentially, looking at the Cordillera of North and South America, pointing out that the elevation of mountain height, peak mountain height throughout this Cordillera sort of lines up with the equilibrium accumulation line of glaciation. When you tend to get above this line, you seem to get eroded back down to it. It's an interesting observation, much discussed. Definitely some caveats. There are cases where glaciation is not erosive if it's cold-based, famously. But it seems there's something, glaciers can erode. This holds up with modern compilations as well. And the other thing glaciers can do that's kind of unique as compared to other erosive mechanisms is they can erode below sea level. So here's one of the deepest fjords in Norway, Sognefjord. The deepest point in this is 1.5 km below present sea level, and granted, sea level was a little lower during say the LGM previous several glaciations, not 1.5 km lower, maybe a few tens of meters. So that's because essentially the glaciers have thickness, they have height, their gravitational potential energy balance it does not stop at sea level, right? And so this is only increased if you do have a widespread, multiple Antarctica, multiple continents looking like Antarctica during a snowball. You're going to draw down sea level a lot, and you can erode below sea level. So in this context, if we think about the hypsometry of Earth today, just how much crust is at different elevations. Well, we've got this big peak right at zero, right at sea level in continental area, which is not a coincidence, right? This is because when you're above zero, you tend to get pulled back down to zero. And if you're below zero, you tend to get built back up with sedimentation because zero is, at least in a fluvial world, that's baseline, that's base level. And down here we have the deep ocean basins. If you go to an LGM, minus 125 meters, okay, a bit more of this is exposed. If you go to a potential snowball scenario, we're talking more like minus 700, minus 800 meters. Potentially the whole continental crust exposed with some gravitational potential energy for glaciers to exploit, for ice sheets to exploit. Um, so there's possibilities here, right? How does the timing look? Well, this is kind of how we stumbled into this. The timing is quite good actually, right? So the start of this excursion is right around the start of the Sturtian. There's probably a little bit of lag time. It takes less than 10 million years at the most for subducted sediment if you put it right into a trench to get into a new magma. So that lines up pretty quickly as long as you do put sediment in the trench potentially, and it seems like this might be the case. Here's again with our covariances. Okay. One question that's sometimes come up since we published this is this signal really robust? As we have all this data, it's not a perfect data set. As we mentioned before, we're missing latitude and longitude, so we can't do the spatial part of weighted bootstrap resampling. Um, the whole problem is if you want to do that, you end up throwing out a large proportion of your data, and then the signal gets a lot noisier. So here's just an example. Let's say we have some true, just think about this as a signal propagation problem, right? Let's say we have some true signal. There's our excursion in whatever our variable is over time. If we generate just mathematically some noisy records from this, which have some Gaussian random noise, some sine wave noise, that signal, right? It's pretty hidden in the noise here, even though we have eight records here. If we recombine these all, our signal is quite clear here, but you would probably not see this if if you reduced your data number by an order of magnitude. This would be a big decrease in your signal to noise. So I don't think we have enough data yet to be able to exclude much of the data on the basis of location. Hopefully, we will in time. One thing we can do, since there's one potential concern with this record, may be that well, a lot of the data at the time of that Hafnium excursion is there's this pulse from Africa, which is basically the Pan-African orogeny. It's also probably where a lot of the subduction zones were at the time. So is this driving the signal? Well, we can't do the full version of spatially weighting, but we can just break things up by continent based on since we mostly have continent level information in the database, and we didn't want to break this up too finely because then again the noise gets you. But if we break this up into three, none of which include Africa here, we've got Eurasia, Australia, and then North and South America. We still have a marked negative excursion at this time in all three. So it's not just an Africa phenomenon. It's much noisier currently if you subdivide the data even this much. But hopefully, we're generating more analyses. We as a community are generating more hafnium and oxygen isotope analyses at a quite high rate. So I'm just going to say time will tell. I think the record that we have is pretty good. Certainly not perfect. And yeah, we'll see. Okay, other lines of evidence. So some of the other ones we mentioned early on, you're coming back to this record that Shannon showed of the continental coverage. So we'll build this up. Here's two not two global records, relatively limited in time, but global. There's Ronov. Ronov always has one of these records, and then there's Macrostrat, right? So both globally and in North America, we have this signal. This is the fact that we have the signal is actually quite intriguing to me, right? Because how do you get up here? This is to be up here. We're really pushing against that spike in our hypsometry to get here. To get most of the continent, 30, 35, 40% of the continents potentially covered by epichronic seas, which certainly fits out with, if you go on a road trip across the US, everywhere it's when this was a shallow sea X hundred million years ago. This does seem to have been the case. It's not the case if you go farther back in time, but it's kind of hard to get here to me from a hypsometry and freeboard perspective, right? If we think about here's our hypsometry again, if we want to have 30 or 40% of what is now the exposed continental crust being covered by ocean, we have to either increase sea level a lot or decrease continental elevation relatively a lot. We have to produce a lot of accommodation space, and the whole time we're trying to do that, the normal sedimentary processes of erosion, removing anything above deposition, filling everything back in are going to be fighting against us. So we need something kind of unusual to get there. We need to produce a lot of accommodation space and kind of rapidly. Again, this could work if we have a lot of erosion during the Cryogenian, let's say. This is just a simple 1D model that we included in that original 2019 paper where we try to model isostases, some thermal expansion traction, and then you do a big impulsive erosion, adjust the amount of erosion until you get freeboard prior to the glaciations. It's near zero. And that gives you these two curves about minus 250 meters of freeboard, so or equivalently 250 meters lower elevation of the continents relative to sea level in either case. And if we translate this through our hypsometric curve, we can turn that into a coverage fraction. And it's certainly not perfect, but it lines up relatively well. Probably the most problematic misfit is back here. So, the transgression, this increase in coverage fraction is not immediate after the Cryogenian. So if that's when the erosion was, something is delaying this transgression. The SOC sequence is there. So if you look at physical examples of the Great Unconformity, oftentimes right below the Cambrian, you have this deeply weathered bedrock. You've got a lot of red things, red and purple, oxidatively weathered paleosols. So we were probably subaerial in the immediate lead up to the deposition of the SOC sequence. So one way or another, for this time, we probably just had not transgressed yet. Why exactly that is, potentially a lot of causes, and I don't have a definitive answer for that. But nonetheless, an interesting to me, line of evidence that I haven't seen many other alternative explanations for up to this point. Uh, Impact craters are also something we talked about back in 2019. We had this figure at the time from this PASSC database, just looking at what were the number of preserved impact craters through time, with the idea that if these are produced at the surface and they have some finite thickness, which varies based on the diameter, the bigger the impact crater, the thicker it is, the harder it is to erode away all the evidence of it, down to all the shatter cones below the crater floor. So relatively small craters, a lot of those start disappearing, somewhere between the Gascaries and the Marinoan potentially. And the bigger ones, there's very few prior to the Circean until you get up to quite large diameters. In this data set, the only ones older were Sudbury and Vredefort, which are huge, as you probably all know. With a somewhat better, newer database is Schmieder and Kring 2020. Um, plotting this, and also not filtering by uncertainty in case that makes anyone unhappy here. Here's just age of impact crater in the Schmieder and Kring database of crater ages and diameter on a log scale here. So we've got a lot of small ones that the only ones that potentially seem to predate the Crydenian are very, very uncertain, which is an interesting pattern if you think about the statistics of it. And then you only get ones that are resolvably prior when you get up to sort of above 30 or so kilometers. You've got one in Finland, I think that's Yarabubba, and then Sudbury and Vredefort up there. This pattern seems to be holding up with more data, I would say. What else? Thermochronology. This is one of the things we talked about at the time as a prediction. Subsequently, Caelan McDaniel, who was a postdoc at Dartmouth, did a lot of work on this, looking in different places at what is the time temperature signal recorded by various thermochronometers that record the diffusive loss of some daughter isotope, or in the case of fission track, the annealing of fission tracks. And saw in many places a consistent signal here. Subsequent paper, Geology 2022, the same year, probably an even clearer signal from Manitoba. Um, Granted, this signal is not everywhere, and nor should we expect it to be, right? Based on what we expect about if this were caused by the snowballs, we would not expect this to be uniform. It's probably best tested in stable cratonic interiors and by spatial patterns of exhumation. Thermochronology is hard, I will say. And to try to understand this better and see if there are any alternative factors. Is there anything wrong with these inversions? Are these accurate? I've actually started producing my own time temperature inversion software, which is fully open source. All the previous ones, there's some very good existing programs, but they're all closed source, I guess, for industry use. So this is fully open source. You can go look at it. You can see if there are any bugs. Please do. And so far, we're getting very similar results to QTQ, the existing Bayesian inversion. But other than sort of trying to understand thermochron better, I don't have a lot of future plans here. Um, is this plausible? It's a fair question to wonder. Snowball Earth is a pretty extreme event, potentially much of a shutdown of the hydrologic cycle. To some degree, this has been considered at the time Snowball Earth was being established, because a potential objection could have been raised that Neoproterozoic glacial deposits, which are some of the most charismatic ones, we've got big diamictites, we got faceted clasts. Those are all explicitly evidence recording wet-based wet-based glacial erosion. So, is that compatible with a hard snowball? Well, this paper from 2003 said yes. Here's basal temperature across a paleocontinent reconfiguration. Everywhere it's black, that's wet-based. So that's where the base of your ice sheet is warm enough to have liquid water, and therefore where you're likely to have basal sliding, which is their lower figure here, and erosion. So granted, this is not everywhere. It's very hit or miss, especially at the margins. But for broad swaths of the continental interiors, kind of where the Great Unconformity is best, most characteristically seen, the answer is yes. Um, just as another, can we find anything more extreme than Snowball Earth? Well, on Mars today, we have lower geothermal heat flux. Geothermal heat flux is the main thing that makes wet-based ice possible when you have a very cold surface temperature. Mars, we have less of that, and we have probably a -60 average surface temperature, down to -150 C at the poles in winter. And there's a bunch of papers suggesting that we have wet-based glaciation on Mars, either in the recent past or today below the South Pole. So if we can have it on Mars, I think we can have it on Snowball Earth. That said, we should not expect glacial erosion everywhere. If that were the cause of the the phenomenon of this glacial the Great Unconformity. There's going to be no erosion no matter what's doing it if subsidence, tectonic subsidence or otherwise, keeps you below your erosional base level. So, in this figure here, if we just have this grob and it's subsiding below, in this case, ocean base level, well, you can erode off everything above sea level, but you're not going to erode off, you're actively subsiding grob in there. Same idea with glaciers, just your base level is a little lower. And then again, even based on the glaciology, this Donadieu paper, and everything we know about, say, Antarctica, when you get to the margins, a lot of the margins are cold based. So like the dry valleys of Antarctica, incredibly cold based, incredibly low erosion rates. If anything, the glaciation protects the rock that it covers more than erodes it. But then if you move a little bit away to one of these outlet ice streams, well, yeah, you've got lots of erosion there. You're flowing fast and you're wet based. Um, so very hit or miss erosion to be expected at the margins if this is something that happened. And then kind of flipping this around, we should also not expect deposition of glacial sediments everywhere, right? Um, so if we think about the Sadler effect, we have to look at accumulation rates in this like log rate versus log time span space. And if you do this, Parton and Sadler 2016 found that the net accumulation rates during Marinoan and Sturtian are substantially lower than those for modern glacial sediment accumulation. But at these time spans, as they mentioned in this paper, the key limiting factor on your accumulation rate is really your accommodation space. So if sea level was much lower during the Marinoan and the Sturtian than in modern glaciations, I think that goes a fair way to potentially explaining that discrepancy. Even if we did have wet based ice during the snowballs. And again, yeah, from the continental margin perspective, you're going to get deposition in front of your outlet ice streams. You're not going to get deposition where you're cold based at the margin, right? So that's again, the deposition is also going to be very hit or miss if this is what's going on here. Um, so that means you have to be careful about going to one place and then saying, well, we don't see it here, so it couldn't have happened. Okay. So to wrap up, let's come back to our historical context here. So I left out one major paper when going through the historical context, which is this paper, William White, 1973 GSA Bulletin, Deep Erosion by Infracambrian Ice Sheets. And this is basically exactly the same thing we proposed in 2019, only decades before. Um, for context, that White had written another paper the year before, Deep Erosion by Continental Ice Sheets. No mention of anything Great Unconformity like, but still talking about exposed Precambrian basement, so effectively basement nonconformities. Um, White in this paper pointed out that a lot of the places where you have large expanses of exposed Precambrian rock, they were either below Pleistocene ice sheets, so like Canada, Fennoscandia, or the large areas that were not covered by Pleistocene ice sheets. Most of these were actually hit by probably the LPIA, the late Paleozoic ice age. Um, and this is an interesting observation to me. It's almost kind of Wegener-like in a way. It's just, oh, these things line up. That isn't that weird. And this didn't get a lot of traction. And then the subsequent paper, when William White came back, is like, and one more thing. I now wish to suggest that further, the widespread and deeply eroded unconformity between Precambrian crystalline rock and Paleozoic sediment, well, called Lipelian interval, is a similar result of profound erosion by ice sheets. In this instance, ice sheets of Infracambrian age. Um, so that's exactly what we ended up coming to from the zircons. But this paper got zero citations ever. So I think it's probably accumulated more now. I took a screenshot of this a while ago. At the time it had three, starting with our paper. We found this citation while we were going through review, actually, and we're like, oh wow, we were not the first ones to suggest this. And actually it gets weirder from there. So if you remember this Olson paper, proposing the megatides, right? Um, there's this whole section in there on objections to the glacial theory, in which he's basically talks about some evidence that Precambrian boulder beds are not glacial. Um, he never cites who proposed the glacial theory. Um, but this is 1966, so this is several years before the White 1972 paper. If anyone knows who previously proposed this, I would love to know. Clearly, someone. I don't know if this was something that was discussed in conferences and conference abstracts that have not made it into the searchable online literature. But clearly, this idea has been floating around for a while. Um, and clearly, and it has not, is not seen much uptake, perhaps until very recently. So, in conclusion, so hopefully we have a little bit of time left. Uh, I think one of my main points for this talk is I just want to say that consistency in terminology is important. Um, your individual physical unconformity surfaces, if you go into anywhere that someone calls the great unconformity, that surface is probably composite, it's probably diachronous, and it's not really meaningful to discuss a singular origin for all of the physical surfaces. Sometimes I think people have interpreted that's what we mean when we talk about glacial origin and the great unconformity. No, that's does not really make a lot of sense. The origin of the great unconformity as a phenomenon, I think, may be discussed meaningfully, and hopefully time will tell as we continue to gather more relevant information over the coming decades.
And thanks so much. That was very interesting. I did not realize about that history. That's really cool.
Yeah, yeah, yeah. And yeah, please do email me if anyone has any idea who suggested this prior to William White.
Yeah. And if anyone has questions, you can put it in the chat or raise your hand or just speak.
I think we have a hand from Jin Guan. Yeah, go ahead.
Yes, thanks very much for this very refreshing talk. That's super awesome. I just have a question following your thoughts that, the melting of the glacier, changing sea level explains the dramatic increase in sedimentary flux, the continental exposure. Would because there are like 16 kilometers worth of crust materials being removed, should we expect the kind of upper continental crust composition changes over time when you have
Uh,
such dramatic changes? Because one thing I noticed is uh, the half mean tells you the source magma changes.
yeah.
So meaning like the glacial melting, the sediment subducted was actually should happen before that, which is the case. But should
Mhm.
we expect, and do we have evidence, say, in the diamictite of some compositional changes that are relevant
Uh,
and to support this idea? Yeah.
yeah. So, well, I guess so. First, I'd say at any basement nonconformity, you can find plenty of those that have 16 kilometers erosion. It's probably rare that all of that is going to be glacial, right? Many of those basement nonconformities are probably composite. But if we do have the sort of 3 to 5 kilometers that we've proposed, I think the key point is that you're eroding from the continental crust and then putting it back into the continental crust, right? Most of the material that's subducted, a lot of that is going to go right back in, either via relamination or via remelting. So I don't know that there's going to be much secular change in crustal composition predicted by this if this is happening. But I think the signals in the zircon, one could presumably find more similar signals. It's a little tricky again because you're eroding essentially average crust. The isotopic signals are a nice way to do it. Um, but I don't know of like any other data sets that are sufficiently numerous to be able to pick up a signal in such a noisy record. It's a sizable signal, but it's still small compared to the heterogeneity and normal Earth processes.
Yeah, well, I don't necessarily know the answer, but one interesting thing pop up is if we look at the sedimentary sulfur concentration in the modern, uh, compared with the slab or the depleted mantle, the sedimentary sulfur is 4 times higher in concentration than the slab and
Mm,
about 27 times higher than the depleted mantle. And so there's differences, right? Uh,
yeah,
even though the cross material should be homogenized, supposedly homogenized,
right,
you have these processes that precipitate and forming gypsum and pyrite
right.
that has this homogeneity and heterogeneity. So maybe that's a way to
I
test it.
Yeah, fair. I think yes. Except there's a to some degree, this is happening all the time, in as much as that our average um, zircon record is kind of near Chur the whole time. So we're apparently mixing similar amounts of remelting existing crust, presumably, I would say, including quite often. I don't think sediment subduction is unique to this event. I think we have quite a lot of it happening all the rest of the time too. So we just have more of it here. We have a very rapid interval of it. Not that it is not happening on slower rates throughout the background all the rest of the time. But yeah, sulfur was a really good idea.
Yeah, it's crazy, but thanks very much.
Yeah, I think Paul has hand up. Paul, go ahead. I think. Okay, good.
Right. Regarding the sediment accumulation data of Partain and Sadler, it's hard to explain this just by lowering sea level, because that just means the same volume of sediment just moves down the slope. And after all, the Phanerozoic data that they compare with, a lot of that's deep sea sediment core data.
Right. Fair.
Second point is that the thermochronology, you have this area of apparent deep erosion in the central part of Laurentia. It's hard to explain with glacial erosion because in the central area of a large ice sheet, the horizontal component of the vector of motion is extremely small. The ice is moving very slowly, and it's moving mainly downward. So you don't really get much erosion there, particularly on mountaintops, because they stick up into colder ice.
Certainly.
Yeah. So most of the erosion is concentrated in those ice streams in the periphery. And you see that where areas are withdrawn. Where are the Great Lakes? They're around the periphery of the ice sheet. And you see the same thing from the radar in Antarctica, the subglacial surface. Most of the erosion is around the periphery in those fjord-like ice stream areas. The third point is that I suspect that there's a very strong Laurentian bias in, for example, the hafnium data. Because what you say makes a lot of sense if you think the world looks like Laurasia, Baltica, Laurentia. But if you look at it from a southern, Africa perspective, this looks like total nonsense. It's much more likely that the driver that you're seeing is the Pan-African Brasiliano orogenic events associated with the assembly of Gondwana from 8 or 10 pieces. And that, I think, fits chronometrically much better with your data, that it's more related to the assembly of Gondwana than to cryogenian glaciation. Although I will grant you that glacial erosion is very good at spreading, fine dust, fine powder out into the ocean basins. But of course, glacial erosion does that even better when it's not a snowball.
Okay. So the few points there. Let's see. So for the first one, the Parton and Sadler, where does the sediment get deposited? If you lower it enough, would you not say that you would push some of it off of the shelf into the into the oceanic crust where it gets subducted? So you decrease the proportion that ends up surviving on the continental crust.
No, because the sea level fall is predicted in a snowball Earth, according to numerical simulations, is 400 to 600 meters. So that's still on the upper slope. It's nowhere near the abyssal plain.
Oh, just thinking in terms of fractions, but okay. So for the second one, the interior, yeah. So yeah, I definitely agree. You're going to get the most, very clearly, you're going to get the most extreme erosion at the outlet ice streams. The thing that I think is interesting in, say, ice sheet models, and in it shows up in this Donadieu, but also in more recent ice sheet models, is there is also flux. Of course, when you're in the middle, yeah, there's an ice divide, like you're talking about. The ice is just going down. There's no basal sliding, right? Totally, absolutely. But there are also places like, say here, where I would call that a continental interior, right? In this case, that's not a margin, but we're still, we're not in an ice divide here, and we still have notable basal sliding there. So that's what I'm envisioning when we talk about erosion in continental interiors. But yeah, I agree. It's going to be much more extreme there in your outlet ice stream.
That interior area you point to, that's a few meters per year. That's extremely slow.
Fair, yes. So you actually, one of the key points here is that you really don't need extreme erosion rates to produce something like 3 to 5 meters or 3 to 5 kilometers of erosion over the, say, 60 million years of glaciation we have throughout the Neoproterozoic. We're really
Okay.
talking rates that are really quite low. The important thing is just that you keep them up and that you don't resediment where you've been eroding. But yeah, the rates do not need to be high at all by, absolute erosion rate. You're talking like 0.05 meters or millimeters per year. You're quite low in the grand scheme of things, rates to produce this.
But they're lower than background. That's the point. Not higher
Lower,
than the
well,
temporal background.
I think it'll
Period of
depend, but
relatively low erosion relative to what happened before or after.
depends on base level, right? If
Okay.
we were below base level
In
here, then
response
it'll
to
be
white,
faster.
and the beveling of the North American interior, large areas of the Western Canadian Shield are covered by flat-lying or nearly flat-lying Athabasca type sandstones. The Athabasca Basin and its equivalents, the Thelon, the
Yes,
Hornby
yes,
Bay,
yeah,
the Elon in the US, the Baraboo, the Sioux,
right,
quartzones. These are virtually
right,
flat-lying, and
yes,
they're 1.7 billion years old. And
true.
so that shows that that interior was eroded to pretty much its present level, and has not been subsequently deformed since 1.7 billion years. So it has nothing to do with Laurentide ice sheet and the Quaternary.
Sure. So yeah, so
So
I
if you're gonna mention the white paper, the reason nobody cites it is that there was a follow-up paper by David Sugden, which is totally trashed the white paper, and that's why it's completely buried.
so I of course agree
It's an
about
interesting bit of history.
yeah, I of course agree about the Baraboo and all that.
If you look at the geological map of North America, you'll see those big yellow splotches. So
No,
that's
no,
also the
yes.
Athabasca type.
No, I'm well aware of those. The
Well,
idea
okay, but
in the
if you look
context
at a
of the neo
geological map, you can
Can
see
I
that the
finish?
erosion was not cryogenian.
Can I finish? I'm well aware of those. The idea in this context would be that you are re-eroding those sediments in many places during the cryogenian, not that you're necessarily deeply incising the basement, right? We're not necessarily saying that in that paper that all deep incision of the basement was caused by the cryogenian glacials. It may just be you're scraping off pre-existing sedimentary cover in many places, right? The hafnium and oxygen isotope signals perhaps work best actually if most of what you're eroding is pre-existing sedimentary cover, not deeply incising into the basement.
The depth of quaternary erosion matches pretty well with the volume of sediment. It's a few tens of meters integrated over the quaternary. A few tens of meters.
I don't have much comment on the Laurentide.
Well, you
Maybe we
cited the
can
white
move on a
paper,
little
though.
bit. Sorry, maybe we should move to give space to other question, if anyone has some more, just in the interest of time. No rush.
So Nick, Christy Blick had a comment. Um, Nick, do you want to expand on it, or it was unconformity? When conformity being discussed and not diachronious, think in terms of Wheeler diagram. Maybe Nick left already.
Yeah. So yeah, I guess the terminology again will come up. So synchronous, if we're talking about unconformities that span the Cambrian boundary, then yeah, definitionally synchronous in that sense. But I wouldn't want to claim that all the erosion that produces those is necessarily synchronous, right? And that they have different starts and ends, but even though they span the same time. So yeah, a terminology question there.
Okay.
Yeah, I'd just like to add, it was a really good and fair and balanced presentation.
Thank you. Thank you, Paul.
So I'm just wondering, so uh, you notice that there is a delay in sea level rise, and I'm just wondering if it's
Yeah.
all related to erosion during Cryogenian. Wouldn't you expect perfectly preserved Ediacaran through Cambrian boundary and actually unconformities
Yeah.
below Ediacaran?
Yeah, so clearly that doesn't line up. I think there are some interesting possibilities if you think about advecting the geotherm during erosion during the cryogenian. There may be also things in terms of, there is some glaciation continuing probably to some extent throughout the Ediacaran that might help to keep sea levels low relatively. You don't need to have any more erosion if you just manage to keep these sediments above base level or keep the eroded surfaces above base level until the sock sequence. But yeah, no, I don't have an answer for that one. But I think we need something that explains the sediment coverage fraction increase to begin with, and all of the Ronov and Peters data.
Well, the Pan-African Brazilian Assembly of Gondwana, I think, fits the timing better.
It definitely fits the timing better. But I don't see how that gets big enough in magnitude. That we don't see this any other time in Earth history.
Orosirian is what it looks most like it.
Okay.
But didn't you have like another zigzag or kind of in
Ah.
Phanerozoic?
Oh yeah, we can look at the figure again. Yeah, there's maybe there's this, right? So
Yeah.
that could be break of sure. It's not quite the same though, and there's this increase here probably has a lot to do with that's the Cretaceous interior seaway on many continents and may have to do a lot with spreading rate being high. So if you take that out, then the overall trend is a little less a little less up and down. But yeah, no, I mean tectonics has a large role here, and even in the cryogenian case, this would not be in any way uh, uh, exclusive with tectonic forcings, including things to do with Pan-African.
I'm wondering if you consider like if it's all related to cryogenian erosion, wouldn't you expect that going back in time you actually will have increase in preservation?
Yeah. So essentially depending on how effectively stratified underlying sedimentary rocks are, yes, maybe or maybe not. Depends on how well mixed the Precambrian, early Precambrian sedimentary rock record is. There are some versions where we go a little farther back, and there are some other higher points actually. So there may be hints of this. I don't think I have this version in here. Um, no, I don't think I don't know that I have a long enough version here. Um, but I think they're in the 2019 paper. Going further back, there are some previous humps, and there's also potentially some interesting signals around the time of sometime between 2 and 2.5 GA, which are harder to interpret to me, but also interesting.
Cool.
Yeah, now that you've got those pictures up, I think that that's a very interesting, that increase in sediment area or volume around 500 million.
Mhm.
And if you look at Laurentia and you look at northern Gondwana, you see the same thing, but the nature of the sediment is totally different.
Yeah.
In Laurentia, it's a big marine transgression, whereas in northern Gondwana, it's this huge alluvial sand sheet that you see all across West Africa, Arabia, and into northern India. It's the main black sandstone that forms most of the north side of Everest, or the south side either.
Mm.
The main part of Everest, Mount Everest, is the same Cambrian sand sheet. So it seems to be a coincidence of two very different phenomena. And I think the latter, the sand sheet, is actually a lot like the Athabasca basin and its equivalents. And I think that this may be related to dynamic topography from mantle downwelling in areas where you have a lot of subduction and the mantle gets cooled and starts to sink, and you have a suction force that allows the erosion mountains to be preserved as these alluvial superfans. And there's been a fair bit of the idea that these actually fit together and covered enormous areas, which raises an interesting question as to their subsidence mechanism. And I think that dynamic suction actually makes a lot of sense, and it's related to the assembly itself. So from subduction feedback, creating a suction which draws things towards it. And you see this for Nuna, Rodinia, and Gondwana, but not for Laurussia or Pangaea. And the difference is that in the older ones, you have multiple ocean basins, including at least one that was quite wide. Whereas in the assembly of Laurussia and Pangaea, you're actually closing a single ocean, the Rheic Ocean, two different arms of it. And so there was much less subduction involved. So the ambient mantle was cooled less. And so this suction force was absent, or at least much less significant. So in the case of the Cambrian, it might be the coincidence of two quite potentially unrelated, or maybe they are related phenomena. But it would be important, whether or not they're related, and they might be, to recognize that they're quite distinct.
I think it's going to be challenging to get enough magnitude of subsidence by dynamic topography, but it'll be really interesting to see geodynamic models of that.
Of course, it's amplified by the sediment load itself.
Fair, fair.
So we're a couple comments. Carol Deller said, for a broader time perspective, see, for example, first NATL 2024 GSA bulletin, see figure 1, lots of erosion prior to the Cryogenian. I don't know if, I guess it was a comment. I don't know if, probably you don't have any reply. Francis McDonald mentioned C. Tassistra, Hart, and McDonald 2024 PNAS. And Shannon Peters, I agree with Paul Hoffman on this one. I have been thinking shifting proportions of ocean subduction versus continent facing subduction. Also, Francis McDonald comment applies.
Okay. All right, I should probably get back to AGU.
Okay. Thanks, Brenhin. It was great talk, and which closed this year, and was a big crowd, over 50 people. And we will restart on January 8th with a full schedule for 2026. Thanks, everyone, and happy holidays. Bye.
Thanks, Andre.
Thanks, Paul.